Hello everyone. In this video, we are going to see the operation of a booth multiplier. The sign multiplication has always been a challenging in digital design, especially when we try to make it as a more fast and more hardware efficient, and then there will be a challenge. So that's where the booth multiplier comes in, a very much clever algorithm that makes sign multiplication is very much fast and simple. Instead of multiplying bit by bit like a normal multiplier, like which we do in Baugh multiplier or normal array multipliers, both algorithm examines or it will check for the two bits alone. It's a pair of bits. It will check for the pair of bits, and if it is 00 or 01 or 1011, so depends on the number, depends on the combination of 0001 1011. It will perform either add or subtract or skip the multiplicand, and then it will effectively reduce the number of partial products and save time. This method works beautifully for 2's complement numbers, allowing both positive and negative values to be multiplied using the same hardware. So where we use the both multiplier? It is widely used in the all the DSP processors and high performance VLSI designs, where efficiency and speed matters most. So in this video, we will learn the algorithm of booth multiplier, and then we will see the examples of booth multiplier within one positive and one negative number, and both are negative numbers and both are positive numbers. So now let's go into the algorithm. So now if you see here, we have got an multiplicand and multiplier. Multiplicand is m and multiplier is q. And then we have gotten two more variables as a and q minus 1 that initially is to be 0 and then count. So it's number of the bits. For an n number of bits, we will perform an uh, n number of steps. That's a count. So it will check for the q naught and q minus 1. If it is 0, 1 or 1, 0. If it is 0, 1, it will perform an accumulator plus multiplicand. If it is 1, 0, accumulator minus multiplicand. If it is 1, 1 or 0, 0, it will not perform either addition or subtraction. Directly it will skip and then it will goes to the arithmetic shift right operation. So once we perform arithmetic shift right, then we will reduce the count to the by 1, and then once the count becomes 0, we will end the algorithm. So it might look complicated, but now we see the example, and then through the example, it will be more clear. So now there is an always confusion tends to happen. How many number of bits should I take? For example, if there is if they have given something called an 8 into minus 11, then there will be confusion that whether I should take an 5-bit or 6-bit or 7-bit. No. So it depends on if we take 4 cross 4 bit, if there are 4 cross 4 bits are there. So when can you take the 4 bits? When can you take 8 bit? So if it's a range of -8 to +7, you can take the 4 bit as an input bits. And then if it is in the range of -128 to 127, then we can go for 8 bits inputs. And if it's the range of -32,768 to 32,767, then we can go for 16 bits. So now, for example, if I have asked you to perform -11 into 12, then how many number of bits we will take? So -11 into 12 in the range of -128 to 127, I will take 8 bits as a input bits. If I ask you to perform -5 into 4, so then it is in the range of -8 to 7, so I will take 4 bits. So now we will see the example. So we have an 5 and then we have an 2. Okay. So now since a 5 into 2, then we can take 4 bits. We can take 4 bits. Why 4 bits? Because in the range of -8 to 7. So it's a 4 bits. Then if you say -11 into 12. So -11 into 12 means what? It is an correspondingly 8 bits, 8 bits. You can see here -11 to 12. It is a range of -128 to 127, so 8 bits. So now we'll say example for the 5 into 2. So multiplicand is 0101 and 2 is 0010. Accumulator is default bit 4 bit 0000, and q minus 1 is 0. So a, q minus 1, which cycle we are. Initially, what is the state? Q minus 1 is 0, q is 0010, so I have put over here, and then accumulator value is 0000. So now I will check for the q naught and q minus 1. So now I will check for the q naught and q minus 1. Q naught value is 0, q minus 1 value is 0. So if it is 0, 0, then what does it mean? No need to perform any addition or subtraction. Directly you can go for arithmetic shift right. So now we will shift the bits by 1 bit portion. So initially the a value is a value is 0, 0, 0, 0, and then q value is 0, 0, 1, 0, q minus 1 value is 0. So after shift right, what happens over here? This 0 goes to this portion, and then this 1 comes to the LSB. This 0 shift by 1 portion, this 0 shift by 1 portion, this 0 comes to the MSB of the Q, and then this 3 bits will shift by 1 portion. Then what about MSB? Arithmetic shift right means whatever in the MSB, it will be get restored once again. So 0 is there, 0 will be restored. If 1 is there, it will be restored as a 1 over in the MSB. So now you can see after arithmetic shift right, 0, 0, 0, 0, 0, 0, 1 and 0. You can see here right, after arithmetic shift right, 4 zeros, 0, 0, 0, 1. So first cycle is over. So now we will check for the second. Now q naught is value is 1 and q minus 1 value is 0. So if it is 1, 0, what we'll do? We'll perform subtraction. A minus m. We'll perform subtraction. So now here a minus m. So a is 0, 0, 0, 0 and m value is 0, 0, 1, 0. So if you take 2's complement, how it will be? It will be and 1 minus m minus 2. So 1, 1, 0, 1 and add 1. So 0, 1, triple 1, 0. So that's the value of an m. So sorry, it's a q. Okay, so I have made it wrong. So 0, 1, 0, 1. So for 0, 1, 0, 1, take 2's complement, it becomes 1, 0, 1, 0, add 1. So 1, 0, 1, 1. So simply we can add the corresponding value. So the m value is 0, 1, 0, 1. So it becomes, if we take 1's complement becomes 1, 0, 1, 0 and add a 1. So it becomes 1, 0, 1, 1. Because why we are doing? Because a value is already 0. So now we need a minus m. Minus m is minus 5. Minus 5 value is 1, 0, 1, 1. So a value has been updated to the 1, 0, 1, 1 after performing a minus m. A value is 0 minus m minus 5. 5 value is 0, 1, 0, 1. Take 1's complement 1, 0, 1, 0. Add 1. So 1, 0, 1, 1. So minus 5 value we have got it. That's a 1, 0, 1, 1. So then once you perform minus operation, then you need to perform arithmetic shift right. So 1, 0, 1, 1, triple 0, 1 and q minus 1, 0. So now this 1 goes over here. Shift by 1 portion. This 1 comes to MSB and then 1, 0, 1. So here MSB will be refilled by the same bit of the MSB. So now you can see here 1, 1, 0, 1, 1, triple 0 and then 1. So now second cycle is over. The third cycle we will compare the q naught and q minus 1. It is 0, 1. So if it is 0, 1, what we will do? We will add the, if it is 0, 1, we need to perform a plus m. So now here what's a value? A value is 1101. A value is 1101 and m value is 0101. M value is 0101. So now add both the values 1101 and then 0, 1, 0, 1. We will get the value as a 0, 0, 1, 0. So it has been updated to the 0, 0, 1, 0, and Q value is 1, 0, 0, and then 1. So now what we'll do, we'll perform arithmetic shift right. So now this 0 goes over here and then shift by 1 bit portion. This 0 comes to this MSB and then shift by 1 portion, and whatever in the MSB will be get refilled. So it is refilled over here. Then the last step. Why is the last step? Because the 4 bits means we need to perform 4 cycles. So first cycle is over, second cycle is over, and third cycle is over. Fourth cycle, Q naught, Q minus 1. So now what happens over here? It's a 0, 0. So no need to perform any plus or minus. Right away go for shift right. So 0 goes over here, shift by 1 portion. This MSB comes over here, and then shift by 1 portion. The MSB will be gets refilled in the same position. So this is the final step. So we have got it. So now check for the output. So 2 power 0. So what's output is going to be 2 power 0, 2 power 1, 2 power 2, 2 power 3. 2 power 3 is 8 and 2 power 1 is 2. It's a 10. So the output is going to be A value is 0, 0, 0, Q value is 1, 0, 1, 0. This is the output. So 2 power 0, 2 power 1 is 2, 2 power 3 is 8. So 8 plus 2, it's a 10 value. This is the final output. So this is for two input positive numbers. So I will go for an 8-bit. So 8-bit means it's a minus 11 and 12. Minus 11 and 12. So since it is a minus 11, we have indicated by means of 2's complement value. So if you see here, if it is 1, 0, 1, 1 is the 11 indication, right? So since it's in the range of minus 11 and 12 is in the range of minus 120 to 127, we should take 8 bits. We need to perform 8 bits, minus 128 to 127. So minus 11 and 12 in the range of minus 128 to 127, we can take 8 bits. So now here what we will do, so 0, 0, 0, 0, 1, 0, 1, 1 is for 11. So I want implicant in the 2's complement. So what we'll do, take 1's complement, 4 ones, and then 0, 1, 0, 0, and add 1. So 4 ones, 0, 1, 0, 1. So this is a value for minus 11. So you can see here 4 ones, 0, 1, 0, 1. Minus 11 and 12. So as usual, accumulator value is 8 bits, 0, 0, 0, 0, and Q value is multiplier value, 12 value. So this is the multiplier value, 12 value we have put over here, and Q minus 1. So now what we'll do, we'll perform Q and Q minus 1 comparison, 0, 0. So no need of any addition or subtraction, straight away we'll go for arithmetic shift right. So shift by 1, 1 positions, shift by 1, 1 positions, and then same MSB will be replicated in the vacancy position. So next cycle, once again 0, 0. Once again shift by 1, 1 position. So after shifting, we have got this. And then the third cycle, it is Q naught is 1 and then Q minus 1 is 0. If it is 1, 0, we have to perform A is equal to A minus M. A value is already full of 0. So minus M. Minus M means A minus of minus 11, because the input variable is 11, minus 11. So minus of minus 11 is A plus 11. So what's 11 value? It's a 1011, 1011. So we have got 1011. Okay, so now after 1011, once you perform subtraction, we need to go for shift right. So shift by 1, 1 positions. Shift by 1, 1 positions. And then the vacancy portion is filled by the same MSB. So now once again it's a 1, 1. So if it's a 1, 1, no need for any additional subtraction, straight will go for shift right. So after shifting, we have got this, and then 0, 1. If it is 0, 1, we need to perform A plus M. So A value is 0, 0, 0, 0, 0, 0, 1, 0, and then M value is minus 11 value, 4 ones, 0, 1, 0, 1. So both add it up 1 1 1 0 4 ones. So we have got this 4 1 0 triple 1 1 1 0 0 4 zeros and then 1. So once you perform addition, then we need to go for shift right. So shift by 1 1 positions, shift by 1 1 positions. So now the same m must be come to the vacancy place. You can see it over here. So once again, after shifting, once again q 0 q minus 1, once again 0 0, shift right. Once again 0 0, shift right. Once again 0 0, shift right. So after 8 cycles, we have got this as the output. What is the output over here? So what's the output? We have got 4 ones, 4 ones, 0, triple 1, 1 1 0 0. So take 2's complement. So this will be full of zeros, full of zeros. 1 triple 0 0 0 1 1. Add 1 1 1 0 1 1 1 0 1 0 triple 0 and 1. So 2 power 0, 2 power 1, 2 power 1, 2 power 2. 2 power 2 is going to be 4 and then 2 power uh, 2 power 7. So 2 power 7 is going to be 128. So 128 plus 4 is going to be 132. So we have got the correct answer for minus 11 into 12. So which we have got in the 2's complement form. We have taken we have taken 2's complement once again, and then we have verified that the output is correct. So this is how we can perform multiplication for signed numbers by comparing the bits. Simple q0 q minus 1. If it is 0 0 1 1, no need to perform any plus or minus, straight away go for arithmetic shift right. And then if it is 0 0 0 1, you need to perform correspondingly a plus m and then shift right. If it's 1 0, perform minus and then perform shift right. So how many cycles you need to perform depends on the number of input bits. If you take number of input bits as 8 bits, you need to perform 8 cycles. If the input bits are 4 bits, then perform four cycles. And then it depends on the input range. If the input bits are with a range of minus 8 to 7, then you need to perform 4 cross 4. We can take the input bits as a 4 bits. And if the input is in the range of minus 128 to 127, then you can take the 8 bits as the input. So this is how you can perform both multiplication. So through this video, we have seen algorithm of both multiplier, and then followed by we have seen for an simple 4 bits, and then we have seen for the 8 bits with a minus number. Thank you for watching.